In this example, we're given three vectors. So v1 is the vector 1, 0, 4. v2 is the vector 0, negative 2, 3. And then w is the vector negative 3, negative 2, negative 9. Now the first question, we're asked to list four vectors in the span of v1 and v2. I'll do that first. So the span of v1 and v2 is the set of all linear combinations of those two vectors. The span of a collection of non-zero vectors, that's always going to contain infinitely many, the dog might bark, just to warn you, that'll contain infinitely many vectors. And that's because we can do, well, okay, so I'm going to list more than four answers, but we could do any number, let's say 6 times vector 1 plus 10 times vector 2. So this is a linear combination, just any number times vector 1 plus any number times vector 2. So in this case, let's see, 6 times v1. If we multiply each entry of v1 times 6, that'll give me 6, 0, 24. Plus 10 times v2, so multiply each entry of v2 times 10. That'll give me 0, negative 20, 30, right? And then combine those. So 6 plus 0, 0 plus negative 20, 24 plus 30. So there's one vector that's in the span of v1 and v2. But we don't have to go to all those lengths. I mean, we could do 0 times v1 plus 0 times v2. And so if you multiply each entry of v1 times 0, that's just going to give you the three-dimensional 0 vector. Plus each entry of v2 times 0, well, that's going to give me 0, 0, 0. And so then the sum will be 0, 0, 0. And so the 0 vector is always contained in the span of a collection of vectors in Rn. So here's one possible solution. Here's another possible solution. Also, the span of v1 and v2 would contain the vectors v1 and v2 themselves, because you could do, well, let's do it this way. I could do 1 times v1 plus 0 times v2. And so that's just going to give me v1, which is 104. So there's another possible answer. And we could do the same thing with v2. We could do 0 times v1 plus 1 times v2. And so that'll give me just the vector v2. And we could also do just any multiple we want of v1 or v2. So something like 0, negative 200, 300. So that'd be the 100 times vector 2. That would be in the span. So you can do any multiple you want of vector 1, any multiple you want of vector 2. Those would all be in the span. All right, and so this first question is really meant to just emphasize the definition of the span of a collection of vectors and to help you see how it contains infinitely many vectors. So that's the answer to question 1 there, or part A here. And there are infinitely many ways to answer this question. So this solution I've written here is not necessarily, doesn't need to be the solution that you came up with. Now part B. Is W in the span of V1 and V2? So I'm going to get rid of part A here so that I can work on part B. So if we're trying to determine is W in the span of V1 and V2, that means that we're asking ourselves, can we write some scalar, let's say A times vector 1, plus some scalar, let's say B times vector 2, and get the vector W as a result. So the question is this equation consistent? That's what we need to determine. That'll help us answer this question. So let's see. If we had A times vector 1, which is 1, 0, let me write this over here. A times vector 1, which is 1, 0, 4, plus B times vector 2, which is 0, negative 2, 3, equal to W, which is negative 3, negative 2, negative 9. Okay, and then suppose I put that in the form of an augmented matrix. And I guess maybe let me show you that whole process. So you take this vector equation. So we multiply each entry here times A. So this is equivalent to A, 0, 4A, plus each entry here times B. So that's equivalent to 0, negative 2B, 3B. And then I'll go ahead and combine those. Hang on, let me write W here. Negative 3, negative 2, negative 9. Combine these so you'd have 1A plus 0 equals negative 3. And then 0A minus 2B equals negative 2. And then 4A plus 3B equals negative 9. There's a system of equations. Okay, well, I was about to write an augmented matrix, but now I'm looking at the equations. I don't really need to. So we already have a solution here. A equals negative 3. We have a value of A. If I solve this for B right here, so take this equation, divide both sides by negative 2, we have B equals 1. We do need to make sure that it satisfies the third equation. Maybe this does, maybe it doesn't. Let's see. So this would mean 4 times A, which is negative 3, plus 3 times B, which we just said is 1. Do these equations satisfy the third equation? Let's see. So does this satisfy the third equation, which would have this equal to negative 9? So we'd have negative 12 plus 3 equals negative 9. Yes, this works. So here's values for A and B that satisfy all three of these equations. And in fact, if I write it this way, let me turn this A into negative 3 times V1, which is 104, plus B, which is 1, times vector 2, which is 0, negative 2, 3. Notice that if we do that, you're going to get negative 3, positive 6. Oh, no, I'm sorry, 0 minus plus negative 2. This is negative 2, thank goodness. And then negative 12 plus 3, that's negative 9. So we do indeed get the vector W. So it works. So that tells us yes, W is in the span of vector 1 and vector 2. And in fact, here we've expressed W as a specific linear combination of V1 and V2. It's negative 3 times V1 plus 1 times V2. There's your linear combination equals W. So that proves that W is in the span of vector 1 and vector 2.